All right, welcome back everyone. This is a Calculus 3. In this video, we are going to talk about 5.3, double integrals in polar coordinates. So we've been utilizing double integrals in many different ways in chapter 5. So one of the way to utilize double integral when you're looking for the area with the polar coordinate equation. So maybe you forgot what the rectangular coordinates versus polar coordinates. So I'm going to briefly talk about the difference. We learned that in chapter 1 long time ago. So here is the great example when you're using the double integral in polar coordinates. So I'm going to show you that example. So let's think about it. In Calculus 3, we've been dealing with two variables of the function. And the circle equation is a great example because when you look at the circle equation, it has x and y, two variable. So if I'm giving you x second plus y second equal to 1, everybody knows that what that means. You have a circle, center is a 0, 0, because I don't see any point next to x and y. And then this is the r square, radius is 1 no matter where you go. So this is a beautifully, you can draw the circle by looking at x squared plus y squared equal to 1. Now, my question is, I want to find out, okay? I want to find out the area, or you can consider this as a disk because we are more like 2-3 dimensional space. So anyway, I want to find out the area of this circle, and mathematically we are using the inequality because that implies the area inside of the boundary of the radius. So in this case, we are using double integral because this function is indicate two variable x and y. And then you must find out two different interval that is respect to x and y so that we are taking the double integral, right? So I told you circle equation is a great one, like a very popular example where you're actually considered to use double integral. So the next step is always you need to find out the interval. Okay, how do I interpret the interval for x variable? How do I interpret the variable for the interval for the y variable? So usually if you have this unit circle, the unit circle means that the point center is a 0, 0, radius is 1. So we have 1 and -1. So that is going to be your interval for x. And then by plugging in, by solving for y, you need to solve for y. And then if you solve for y, I'm going to modify a little bit. Y second is going to be 1 minus x second. So y is going to be plus minus radical 1 minus x second. So this is going to be your interval for the y. So one of the interval, we talked about it, is a fixed. So as you see that if you fix the x variables interval, y variables interval is going to be changing depending on the x variable. So everything is written by x variable to describe the interval for x and y. So we got it. So now you might be thinking, oh, Professor Ben, now I can set up the double integral because I can see the each interval for x and y. So double integral, right? We have a function, let's say fx comma y. So this is going to be the circle equation. And then you can take, y variable, x variable, doesn't matter the order. We know that it's going to be same anyway. But usually dy first, and then these are the y interval. So I know how you're going to set it up. This is how you're going to set it up, isn't it? And then dx is a fixed, is outside, -1 and 1. I know you are going to solve this one to find out the area. Right? You can estimate the area of that circle, right? So this is like an easy question because we can also use a, circle, area formula for circle. But the case is, what if we have a complicated number for the r? Then like taking the double integral will be more accurate to find out the area. So I'm not going to talk about too much. My idea is in a double integral, help us to find out the area of the function with two variables. It could be circle, or it could be, some like 3-dimensional shape. You never know what type of function you're going to have. So my idea here, if you have X and Y, the interval also include either one of the variables. So this is the variable for the Y interval. This is the numbers for the X interval. But again, Professor Ben, I got it. I know how to set up this double integral. This is so clear. But my question is, do you really want to calculate it? Sorry. So what I'm saying is, this interval looks complicated. So chapter 5.3, what they're saying is, instead of using this rectangular coordinate, so X comma Y, we call whatever the variable, whatever the equation or coordinates, you can point out whatever the, any points inside of the circle, we can describe it as X and Y. So that's how we call rectangular coordinates. Those are the coordinates. If you are, indicate the point with X and Y, that's a rectangular coordinate. So we found out some limitation, guys, this is too complicate number. Like you're gonna take the derivative, you're gonna take the integral, and then you have to plug in this one. Like, honestly, this is like too complicate, radical and second power. So 5.3, yes, we are going to convert rectangular to the polar coordinates. We talked about that conversion in chapter 1 at the beginning of the semester. So what if we are converting this one? And then your interval for X and Y should be converted. And then the calculation is going to be much, much simpler. Because look at that. The X now we can consider as the radius of the circle. So if you look at the radius, it's going to be between 0 and 1. And then theta, X comma Y, this is the rectangular coordinator. And then if you are pointing the same position with radius and theta, we call this as a polar coordinate. Do you remember that? So this is too much like work. So we're going to convert whatever the rectangular coordinate to polar coordinate. And then this theta is going to be 0 to 300 degree, which is a 2 pi. So if you change X comma Y to R comma theta, then this double integral is going to be much easier. So 0, 2 pi, and 0, 1. And then here you have d theta, dr, right? So check it out. Which one is much simpler? The second way, polar coordinate, you have always simple like a pi or some radius. Therefore, 5.3, we're going to focus on polar coordinate and take the integral, double integral of the polar coordinates. Okay. So just a little bit of a background in chapter 1. Many people maybe forgot. So recall that polar coordinate is written by radius comma theta. And then this is really related to the rectangular coordinates. If you remember, specifically, we wrote down this formula. R second, radius is equal to X to the Y second. So you can convert it X and Y to the, polar coordinate system. And especially X equal to R times cosine theta, Y is equal to R times sine theta. So you can convert from the rectangular to the polar coordinate because that's easier to calculate, take the integral. Then you can say now, instead of X, Y, the domain for the interval, now we have R comma theta. You're going to find out the interval for R radius, interval for the theta. Then you are going to take the double integral, right? So dr, then you have like a and b. We have a d theta, have a alpha and beta, something like that. So the order can be changed because anyway you're gonna get the same answer. So that's the background. And then specifically 5.3, actually this information modify in modernized math. I'm gonna go down slowly. So don't try memorize the formula. I'm not a big fan of the formula. Just try to understand the storytelling, right? So here, this is exactly we are going to use to take double integral in polar coordinate. So if you satisfy with the interval for each R, if you have that information, double integral. So this is the way. This is the rectangular coordinate. You can convert it to the polar coordinate, and then you're gonna take the double integral. This is a much shortcut and simple calculation. Polar coordinate, and the formula is this one. Okay. So for x comma y, we talked about it, x equal to r times the cosine theta, right there. Y equal to r times the sine theta. So x has been here, y has been here. And then there's a little bit of r, you need to multiply r at the end. So this is a separate, variable. And then you're gonna take the integral with respect to dr first. So this one should be r integral, and then d theta should be at the end. You can change the order, like a d theta first to dr, it's going to be the same answer. But usually this is the popular formula in terms of finding the area based on the polar coordinates. Okay, so that's the idea. We're going to convert the rectangular coordinate to polar coordinate. And then this is the formula to take the double integral to find out the area based on r comma theta. Okay, so I briefly talk about the story why we are not taking integral with the rectangular, because xy function is going to be complicated. Instead of using that calculation, we're going to convert it to the polar, because polar is going to be only focused on radius and theta. So the calculation might be simpler. So I will show you the example exactly. So can I go to the next slide? Let me show you the example, how you can convert the rectangular to polar and take the double integral. So let me take a look at the example. All right, so example 1, definitely we are taking double integral. Okay, and then we are looking for the area D. And then that is region between these two information. And then it is lie on the first quadrant. Whoa. So if you remember long time ago, right, pre-calculus, how to interpret this double inequality. So you have one, right? You see that one equation. So this is one, x second plus y second. And then 4 here. And then this is a greater than. So if you look at the circle, this means the radius is a 2, correct? So you have a 1, 2, 1, 2, 1, 2, 1, 2. So we have a circle, my image. So this is the circle. And then they say greater than, so outside area, it's outside. So that's a one equation you can discover. And second equation, what do you see? The other side, I have x second, y second is less than 25. In this case, radius is 5. So I'm gonna keep drawing here. It should be larger. So 3, 4, 5, 3, 4, 5, 3, 4, 5, 3, 4, 5. So this is the circle. And then they say less than. So inside. So they also say that the area is going to be on the first quadrant. So where is the area? Outside of the first equation, inside of the second equation. This is the area we are looking for. Are you clear? So this is outside area. So when you look at this equation and inequality, you should be able to draw where is the region we are looking for. We are looking for that region. Okay, we good. Now we are going to convert whatever the x comma y in terms of the r comma theta, because that's easier. As I mentioned, always it's an easier way to calculate or take the double integral. So I'm gonna keep going. We got it where we are looking for. We're looking for this area. So in, see my laptop, okay, in polar coordinate, right? We have to create the interval for r comma theta. And then you're gonna find out the interval for r. Also, you're gonna find out the interval for theta. Okay, First thing, you can easily catch the data. The circle is always going to be 0 to 2 pi. So here is a 2 pi, but you know, the circle data is between 0 to 2 pi. But you have to keep in mind, this area is only in the first quadrant. So this is the angle we all have. So that's going to be what? 90 degree. So you can divide it by 4. So each quadrant has equally likely 90 degrees. So you can divide it by 4. But you don't need to divide it here because we're already looking for the data. So simply just divide it by 4 here. So we are looking for the, 0, 0. This is a 0. The data we are indicating, it's going to be from 0 degree up to 90 degree. As a radian, it's going to be 2 divided by 4 is a pi over 2. So your interval for data in first quadrant, it's a 0 to pi over 2. Beautiful. Are you following? I mean, I'm not talking about the entire circle angle. We are talking about the angle only in the first quadrant. So that's going to be 0 to 90 degrees, so 0 to pi over 2. All right, next one, the radius. So the radius, these are the radius, isn't it? So it's going to be between, this is a 2, this is 5. So this is all you have, from 2 to 5. So it's easy to find out. Thank you, Yanni, that's great. So we have a radius, we have a data in the first quadrant. Gotcha, this is your interval, okay? So I'm gonna make a little bit minimize. So now we're gonna take the double integral based on this interval, okay? So if you go up, so we have a double integral. I'm just writing the formula. They say, oopsie, if I go up, showing you the formula, that is equal to f r cosine theta, but we don't need to write down f anymore. Just r times cosine theta. And then this is going to be corresponding to x, right? And then y is corresponding to r times the sine theta. And then I told you, don't forget that r at the end. Okay? And then you're going to write down dr first. So where's the r radius? From 2 to 5. Beautiful. And then d theta, we have a 0 to pi over 2. There we go. You're going to take this double integral. You can set up. You can set it up. That's it. And the rest of work, it's just calculation. So I'm going to do step by step one more time, because this is a little bit couple step we have to think. So if I look at this numbers, I'm going to simplify. So that means we have a 0 pi over 2, 2 pi. We have a 3 r. So r to the third, correct? R to the third, cosine theta, sine theta. I have a dr d theta. Okay, that's great. And then we are taking, so you're taking the integral this part first. We are taking the integral with respect to r. So what did I say, guys? This cosine theta, sine theta, now they are considered as a constant. So it doesn't matter that you can consider as a number. We are focusing on the r. So what happened? Cosine theta, sine theta, keep it because that's a constant. And I do have, I'm gonna take the integral r to the third plus 1 over 4 from 2 to 5, right? And we have still 0 pi over 2 d theta. Are you following? Because cosine theta, sine theta, that's constant. You don't need to do anything, just keep it. And then take the integral r to the third. So let me calculate it. So this is a cosine theta, sine theta. You have r to the 4 over 4 from 2 to 5. Am I right? Okay. Now what are you guys going to do? We are going to, we have to calculate it, but here we can actually think about one more step. You can actually calculate plugging 5 into the 5. So I'm going to keep going. So here, I still have a 0 pi over 2. So what happened? Cosine, so this is a constant, right? So I'm not going to do anything. So cosine sine theta. And what happened? 5 to the 4 over 4 minus 2 to the 4 over 4. And then we have still d theta. Okay, so I have to subtract f of 5 minus f of 2. That's what I'm doing. Okay, we have to keep simplifying. Pi over 2, cosine theta, sine theta. Somebody can calculate it. What you got? 5 times a 5 times a 5 times a 5. Let me calculate it. Sorry. 5 times 5 times 5. 625 over 4 minus 16 over 4. And then we have the theta. So one more time. So 624 minus 16, 609 over 4, and d theta. There we go. Now we're going to take the integral based on theta. So now, this is a constant for sure. So I'm going to bring that all the way to the front. And then we have a pi over 2, 0, cosine theta, sine theta, d theta. Dun, 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 dun. All right, we've been practicing it in Calculus 2. This is, do you remember? I feel something, use substitution. So I'm going to actually bring the last step here. So here, use substitution. I'm going to say sine theta. So du over d theta. If you take the derivative of the cosine, sine, it's going to be cosine. So cosine theta. So du is a cosine theta d theta. So we got it. Cosine theta times d theta. This is du. And then sine u, that was a u. That's my u substitution. So if I collect all that information, so 609, 4. Now we have a u substitution, right? So that I just want to make sure this is the interval in terms of the theta. So theta, we have 0, pi over 2. This is the based on the theta. Because we are using u substitution, you have to convert it in terms of the u substitution. So sine 0 is a 0. Sine pi over 2, it is going to be 1. So it's going to be 0, 1. So now you have 0 to 1, u du. Because the cosine, sine theta is a u, cosine theta times d theta. We just proved that it is a du. Now we're almost done. So 609, 4. This is the u to the second over 2, 0, 1. And then 0, 4. What are you guys going to do? 1 over 2 minus 0 over 2. So this is going to be 0. We have only 1 over 2. 609 over 8. That's the area we're looking for. So convert it to the polar coordinate is much easier because x and y, it's more complicated. You have to solve for y to find out the interval for y. It's going to be complicated. So instead of using rectangular coordinate interval, use a polar coordinated interval. It's much easier, focusing on r and theta. So that area we are looking for here, this, your shape, this is going to be 609 over 8. So that's a 5.3 main idea. If you got this one, we're pretty much done 5.3. 5.3 is a very, very short topic, okay? So I'm gonna hold up here. I'm gonna just do one more example, okay? So take a look at it. If you got that one, I love to see your thumbs up. Okay. So you can definitely manage this type of question. All right, so if you got that one, and just a little techniques, right? We learned from Calculus 1 and 2. One more example, okay? One more example. Here we go, number 2. All right, so this one, we're gonna find out the volume of the solid bounded by the paraboloid z equal to 16 minus 3x second minus 3y second, and the plane is equal to 4. So looks like, okay, doesn't matter. Integral help us to find out area, volume, force. It helps us to find out many things. So anyway, it doesn't matter that even though they're saying area, even though they're saying volume, anyway, you're gonna take the integral. But you have to check how many integral do I have to take. I see you two variable, so it's gonna be double integral, but we have to think a little bit. So the paraboloid shape is equal to 16 minus 3x second minus 3y second, and there is a plane z equal to 4. So I'm just trying to, imagine the graph. So I'm just trying to something like that. So the paraboloid shape is going to be something like a volume up. But do you remember, if we have a z equal to something, the z-axis is going to be open. So the parabolized shape is something like this. We're going to open z, right? So this is going to be something z equal to paraboloid shape, 3x second, 3y second. We good? And then they say z equal to 4. So this is the z. So we have a plane that is passing through z equal to 4. Something here. Something is passing like this. And then if you imagine the paraboloid shape, actually this is the paraboloid shape. So we have a parabola shape up there. And then there should be like, it's a three-dimensional, something like it's here. So we have like that shape. And there's, interestingly, plane is going on. So that's I can approximately draw it, okay? So that's something going on, but we have to catch more information. So z equal to 16 minus 3x second minus 3y second, and z equal to 4. So both of them are z equation, which means they are going to interact at some point. I don't know where exactly, but both of them are equal to z. So you can find out the intersected point. Do you remember that? Yes. So this plane, they're intersected at some point, okay? So let me just think about that more. So this is the given function. This is a paraboloid. And then we have a z equal to 4. So I'm going to set it up. 4 equal to, that's a z. And then that's a z, 16 minus 3x second, 3y second. So let me simplify this equation. Let me bring this 2 to the other side. So positive 3x second, positive 3y second. 16 minus 4 will be 12. Ooh, I can divide it by 3 everywhere. So they are going to be intersected at this circle equation. So if you think about like x and y, so this is x and y. So there is a circle going on only passing through the x and y. So they're exactly somewhere like a radius is going to be radical 12. So they're going to be some circle inside of the paraboloid and inside of the rectangular. This is their intersected point. This is their common area. Does it make sense? Because this is like three-dimensional space. So it's the same concept. There's a paraboloid, the pink shape going on. And then there is a z equal to 4. The plane is going on. And then we found out this is the intersected between two different shapes right there. This is a common area. So this is circle is a part of the pink paraboloid, but also it is a common area of the plane shape. So this is something going on. All right, so we have x second plus y second equal to 12.
Excuse me.
Oh, yeah, I made a mistake, 4. That's what you're going to say? Yeah, 4. I divided by 4. Divided by 3, so we have to get 4. So yeah, that's a better. So the radius is a 2 exactly, so that's much simpler. All right, so that's something we got, okay? So this is something I can find out, and then let's step by step. As you know, this is x, y. This is a rectangular coordinate points. There's no r, there's no data. So honestly, how are you going to be able to find out the interval for the X? It's complicated, right? How do I find out the interval for Y? It's complicated. So I am going to anyway change it to the polar coordinate system. So let's step by step. We are looking for the volume. And this is the f comma xy. So we have 16 minus 3x a second, 3y second. And then we do have we do also have a 4. So we have to a little bit think about it. So this one, let me think about it. This is fx comma y, but we have to also consider this is equal to 4. So what I'm saying is, if you have two functions going on, we are looking for the volume between them. So whatever the one of the function minus second function. Do you remember like the area between two function, right? Let's say this is f of x, this is a g of x. I'm looking for the area between the common a to b. We take the integral f of x minus g of x. So we have two things going on, okay? Although there's no x comma y, this is coordinate points. Sorry, this is a rectangular points. So we have to subtract some function minus the other function. And obviously the height of the paraboloid is higher. If you're plugging in any number, it's higher than 4. So this function minus 4, then we are actually taking the double integral to find out the volume. So this is the in terms of the rectangular coordinate points. So as I told you, it's hard to find out the interval. So we're gonna step by step to convert it to the polar coordinate. But first, I'm gonna simplify this function because that's a better always simplify. So 16 minus 4, I have a 12, 3x a second minus the 3y second dA. Okay, nothing is special yet. It's a still rectangular coordinate form. I'm gonna keep simplifying. Now I can do something. The fact r second is x second plus y second. Do you remember? If we go up, we're gonna utilize this fact. So I need to convert from rectangular to polar. I don't want to see x and y anymore. So watch me. We have 12 minus 3. You can find out the common factor. And then x second, y second, dA. So this part is going to be r second. Am I correct? So I'm trying to convert it to the polar in terms of r and theta. So 12 minus 3r to the second theta. That's it. This is what? Fx comma y. This is going to be f r comma theta. Nothing we can do anything. So let me just make a space. You have to a little bit. So we found out r theta. So now we can find out the volume in terms of the polar coordinate. This is a polar coordinate system. Double integral, right? And then I do have 12 minus 3r second. And I told you, don't forget to multiply r at the end in the polar coordinate systems double integral. So there's r at the end. And then now you could do, take the dr first and d theta. So I'm going to show you one more time the formula right there. There's r. So we converted this one into the r comma theta. This is not going to be r cosine theta or r sine theta because we just converted this fx comma y into the f r comma theta as 12 minus 3r second power. Then I multiply r and dr and d theta. That's it. Now we could do the interval. So the interval part, so dr, that's going to be here. D theta, it's going to be here. And just so you know, theta is going to be 360. So always, if you don't have any restrictions saying that it's going to be only one quadrant, first quadrant, second quadrant, it's going to be always 0 to 2 pi. Because that's a whole area, sorry, whole angle. So it's going to be 0 to 2 pi for the theta. Now the question is the radius. Do we have any radius information right there? So from here, Radius is a 2, so we have 0 to 2 for the radius. So you are using the given information we found out. That's it. That's how you're going to find out the answer. You're going to take the double integral based on this polar coordinates. So I try to show you, we just converted, the given information was a rectangular coordinates. So I try to convert it to the polar coordinates. So find out which one can be r, which one can be theta. Theta is really easy because it's a 360, so we don't need to really care about that. But this is all we have, right? You can simplify. And then I plugging into the polar coordinate equation, and don't forget the r. That's it. You need to take the double integral right there. So we're gonna do this part first. I'm gonna multiply r first everywhere. So 0 to pi, 0 to 12r minus 3r second, dr d theta. So now I'm gonna take the integral with respect to r. So there's nothing constant. Everything has r. So that is gonna be 12 r to the second over 2, 3 r to the third over 3. We have a 0 to 2. And then we have a 0
Excuse
to
me.
Yes.
It should be 3r cube.
Yeah. Oh, sorry. Thank you. So this one should be, yes, this is a second. Oh, actually, this is a third. Yeah, second power times 1. So I made a little bit of mistake there. 4. Thank you for checking. Yep, this is better. So we're gonna simplify inside. 6r to the second, 3 over 4, r to the 4. And 0 to 2, so we're gonna 6, 2 to the second, 3 over 4, 2 to the second, and everything is gonna be 0. So that's gonna be inside. So if you calculate it, this is a 4 times a 6 to 24. 4 cancel 3, so this one is going to be 21. Am I correct? So now we are going to still take the integral outside. Integral 2 pi 21 d theta. That's what you need to do. Am I correct? All right, so we are going to simplify, right? So what are you guys gonna do? Let me just look at that 21 theta. So we have to take the integral. This is a constant, increasing
Excuse
the theta.
me.
Yes.
The 2 should be to the power of 4, not 2.
Oh,
No second
yes.
power.
Sorry, I'm keep making a mistake. Let me go back. Yeah, you're right. I don't know why I put the second power. So let me go back. It's gonna be 4. Yep. So let me just recalculate it. This is gonna be 24, definitely. And 3 over 4. 2 to the 4 is a 16. Yep, so that's gonna be 4. So we have a 24 minus 4 times a 3, 12. I hope this is a better. Yeah, there we go, actually 12. So now we are taking 0 to pi d theta. Yes, actually this is right. Now we are increasing 12 theta, taking the integral 0 to pi. So 12 times a 2 pi minus a 0. The answer is a 24 pi. That's the area we're looking for. Okay, a little bit challenging, but you can think about it. Okay, so that one was the second example that I wanted to share with you one more time. All right, so far we talked about how to convert rectangular to polar coordinate, and then definitely the integral for the 2 different variable is going to be respect to r and theta. Okay. All right, so I'm gonna do just a couple more example, but in this time, we are going to use another integral if you have like some complicated function. So can you show me your thumbs up? Are you guys okay with that so far? So if you got that one, if you got this one, okay, sounds good. I see a couple thumbs up. Are you guys okay? All right, so take a look at it. Okay. Let's talk about the next one. So let me go to here. Okay, here we go. So sometimes you might be seeing more complicated function in terms of the polar coordinate system. So what I'm saying is, this is for sure. If f is a continuous on the polar region, we have r comma theta. So you have a theta interval, and you must have r interval, right? But sometimes the r interval is written as some function. It's not simply like 2 to 5 or 3 to 6. Sometimes it is going to be written by like equation. R is going to be changing depending on the data. So in this case, nothing is special. We do have the same x comma y. You're going to convert it rectangular to polar coordinate and multiply r here. You're going to take dr and d theta in terms of the integral, but you need to be careful with the radius interval. The radius, you need to reevaluate the radius interval in terms of the function. So I will show you that example, what that means. But the formula is the same thing. Nothing is special. You're converting the rectangular to the polar, right? But what if the radius function is given with the function with related to theta and r? So this is something. So what I'm saying is r is not something like a radius, 5 to the second, simple number. It's going to be more complicated, like a function. So step by step, I do have this function. This is a rectangular because I do see x and y. I want to convert it to the polar. So here in polar coordinates, we do have, this is a rectangular. We're going to convert it to the polar coordinates. And then the equation must be changing, but here we go. This one, we can already change it to r second power. We know that x second, y second, r second. So we can do, so here's a double integral. And I do have radical r to the second. So basically it's r because the radius and second power will cancel. And then keep going. We have to multiply r and then dr d theta. Are you following? I just converted this part. R to the second, radical is just r. So we have r actually. So I'm going to cancel. It is going to be r. I just converted. I hope you understand this, right? So I literally convert rectangular coordinate to polar coordinate. Are you okay with that? So we know this fact. Therefore, radical x second plus y second is the same as r. Now, we have to look at the interval, correct? So I told you theta is nothing you need to worry about. It is going to be 0 to 2 pi. The question is the dr, the radius for the r. So this is like something given, right? And the radius should be positive number. So we are going to write 0 and here 1 plus cosine theta. This is the radius for the r. Are you okay with that? So I'm not changing anything. I'm just using the given information. So what happened? This is what you need to do. So I'm going to rewrite it. We are calculating 0 to 2 pi, 0, 1 plus cosine theta, r to the second, dr d theta. That's what we are going to do. Beautiful. So same step, take the integral inside. What is it? So we have r to the third over 3, 0, 1 plus cosine theta, and then 0 to pi d theta. And then I can complete the next step. This is going to be 1 over 3. We have a 1 plus cosine theta to the third power and minus 0, that's 0. And then now you are going to take the integral d theta. Whew, we got it. All right, now we have to do the work So we have a 1 plus cosine theta to the third. Can you expand it? So 1 plus cosine theta to the third. If you expanded it, it is going to be 1 plus, what is it? If you take the integral 1 plus, or we can calculate it. It is going to be, let me just multiply 3 times actually. I know it's a little bit of work, but 1 plus cosine theta, 1 plus cosine theta, 1 plus cosine theta. So 1 plus 2 cosine theta, cosine second theta, that's the first 2 multiplication. And another, I'm gonna multiply one more time. So 1 plus 2 cosine theta, cosine second theta plus cosine theta. So I'm just using all the distributive property, plus 2 cosine second theta, cosine third theta. Whew, okay. So I can do combining like term 1 plus cosine, 2 and 1. 3 cosine second theta. I have a 3 cosine theta and cosine third theta. So this is what I got. So I'm going to move this a little bit here. So this is a little bit of calculation you can conduct. Now I'm going to plugging in into right there. Yeah. So I'm going to make a little bit small space. So now we have integral 0 to pi 1 over 3. And this part, right? This part, we just found out 1 plus 3 cosine second theta, 3 cosine theta, cosine third theta. And then there's a d theta at the end. Okay, awesome. Just a little bit calculation, right? And then what happened? I can multiply 1 over 3 everywhere. So 0, 3 pi, 2 pi. And then 1 over 3 plus 3 cancel, cosine second theta. 3 cancel, cosine theta. We have a 1 over 3 cosine 3 theta and d theta. There we go. Yeah. All right, what are you guys gonna do now? We are taking the d theta integral. Yes, so we are going to take the integral. So first one, you can separate everything. So separate it. This means 0 to pi 1 over 3 d theta, 0 to pi cosine second theta d theta. I know it's a lot, but we can finish. Cosine theta d theta, 0 to pi 1 over 3 cosine third theta d theta. So that's all you need to calculate it for the rest of the part. So this one, 1 over 3 theta, 0 to pi. And then cosine second theta, just be aware, we talked about it. We can change it to the double angle identity. Cosine to theta is the same as 1 plus cosine 2 theta over 2. So that's the same. So we have 0 to pi d theta. And cosine theta, if you take the integral, what is it? Cosine theta, if you take the integral, anybody remember? Somebody can tell me. It's a sine theta. So it is going to be just a sine theta, 0 to pi. And then I have 1 over 3. So many people a little bit confused. I'm going to bring 1 over 2, 3. Cosine third, I can convert it to cosine second theta times cosine theta, d theta. So they are same. I just break them into 2 and 1. So a little bit of work, I'm sorry. So we know you can calculate this part. It's going to be 2 pi over 3 minus 0 is a 2 pi over 3 plus, here you can separate it 1 over 2 and this part. So integral 2 pi 0 1 over 2 d theta, 0 to pi cosine 2 theta over 2 d theta. And this is going to be sine 2 pi minus sine 0. And the last term, that's something I want to write it. So here we have a 1 over 3, 0 to pi, cosine second theta. Remember, this is the same as 1 minus sine second theta, right? And then we have cosine theta d theta still there. So they're the same. Because a cosine second theta plus a sine second theta is 1. So hang in there, almost done. So this is a 2 pi over 3 anyway. And then this one, you can do 1 over 2 theta, 0 to pi, just calculation. And then I can bring 1 over 2 to the front, 0 to pi, cosine 2 theta, d theta. Now you can take the integral, right? Sine 2 pi is a 0, sine 0 is a 0. And 1 over 3. Here we have to do something. So I'm going to say use substitution a little bit. So u equal to sine theta. Du over d theta is cosine theta. So du equal to cosine theta d theta. So this is going to be du because of the substitution. So I can do, say, we have a 0 to pi, 1 minus u du. Are you following? Because we just use a u substitution. So hang in there. 2 pi over 3. And then 1 over 2 pi, and then minus 0, because 1 over 2 times 0 is a 0. And then we have to take the integral. So this is the integral. Do you remember? This is going to be, you're going to flip over. You're going to flip over 1 over 2 and sine 2 theta from 0 to 2 pi. So we have still 1 over 2 in the front. So this is how you're taking the integral. Go back to the integral table. So you're going to flip over whatever the constant and then keep 2 theta. And then plus, this is a u substitution 1 over 3. And then 1 minus u, right? What are you guys going to do? We are going to take the integral. So this is 1 is going to be u to the second over 2 from 0 to 2 pi. Whew, it's a lot, I know. Almost. 2 pi over 3. This is going to be pi over 2. Actually pi, because 2 to cancel, my bad. So my bad, this is just pi, because 2 pi divided by 2 is pi. And this is 1 over 4. And then we have a sine 2 pi minus sine 0. Again, they are going to be 0, right? So sine 2 pi is a 0, sine 0 is a 0. That's all 0. And then here, 1 over 3, we have a 2 pi. Oh, actually, I have a little bit of mistake because we have, always I made a mistake here. Because the 0 to pi, this is in terms of the theta. We have to convert into the u variable. So sine u, so sine 0 is a 0. Sine 2 pi is a 0, so 0, 0 actually. You see that? Because we use a u substitution. So 0, 0. So here, instead of using 2 pi, we have 0, 0. So actually, it's a 0, nothing. There's no area between 0 and 0. So this is all going to be 0. So you don't need to even write it. That's a 0 again. So therefore, the final answer here, 2 pi over 3 plus pi, because this is also 0 and 0. So the answer, if you calculate it, 3 over 3, what is it? 2 pi over 3 plus 3 pi over 3. We have a 5 pi over 3. That's the final answer. Woo, we got it. I double checked the answer. We got the correct answer. Sorry, it was a long work, but the final, I'm not going to put that kind of question, but I just wanted to show you. This is how you're taking the double integral, the same strategy, double integral with the, more complicated long process. But, the step is you need to know how to convert from the rectangular to the polar coordinate. That's the main idea. And then the rest of the part is just calculation. So it should be okay. But I'm going to hold up here. You might have a question. So that's what we got. So whatever the question, it's the same pattern. You can set up the equation and you're going to do the calculation part. So we're almost done. So this is the one thing you can think about. And I just have two last questions. If you're ready, I love to see your thumbs up. Does it make sense to you so far? Are you guys happy? Does it make sense? I hope so. So I see a couple thumbs up. So take a look at it. So I show you all the steps. So this is a clear, should be okay. But let me go to the last one, the last example. So sometimes, okay, so there are three different versions of the equation. So let me just go up. If I go up at the beginning, so this is the first one. So this is the equation, how you convert from rectangular to polar coordinate. And I show you the second one. If the radius is a given the function, the integral is a given function, nothing is special. The formula is the same, just you need to be careful with the integral of the radius. The last case is, it's better. So for example, we have a same goal. We are looking for the area of the polar region. So your function is going to be r and theta. And then one thing is, everything is the same. One thing is, this is the second version. This is the second. Doesn't matter. You can use the other formula, but this is a second version of the formula. So depending on your choice, you can use it, but I'm just showing you because it is sometimes a simple version of the same polar coordinate formula. Okay, so you have to find out the area. So instead of doing find out the radius, find out the radius for the integral for the radius, integral for the theta, this one you can do it, but this is the same as second formula. Either this one or either that equation, you will get the same answer. So far, I've been focusing on using this formula, but I'm going to show you, use the second formula. This is not going to be double integral. Okay. If you have a theta function, only the theta function. If you have a theta function, square of it, just take the integral with respect to the theta integral. That's it. So let me show you the example. So example 5. So we have the region, we want to find out the area. And then they are close by cardioid are equal to 1 minus sine theta. Okay. So let's think about it. This is already given, right? And then r equal to 1 minus sine theta. It means what? F theta equal to 1 minus sine theta. Does it make sense? Because if you're changing the input, you will get the different output, right? So doesn't matter. So I'm going to just corresponding. They're same. R can be f of the theta. So this is actually given f theta. So therefore, you can do it. You can use this formula. Doesn't matter. You can plugging in 1 minus sine theta and times r, but there's no commonality. So what I'm saying is, if you're double, so I have r, right? dr d theta. You can continue, but it's hard to find out the radius, integral, and other things. So instead of using it, This formula is the same as half one integral, the integral of the only f theta d theta integral. So I'm gonna just go back. So we just found out that this is the f of theta. So you're gonna just plugging in here. Therefore, 1/2, the area, we have to define what the theta, what the integral, but the theta is given, 1 minus the sine theta, d theta. And what did I say? If you have theta, it's always 0 to 2 pi. And then here, we are going to have a second power. That's it. This is the same. You will get the same answer. But the problem is, this is, we don't know the integral. It's more complicated. So therefore, this last version of the formula, it's a simpler because you have, if you have f theta function, everything is clear because the theta integral is always 0 to 2 pi. So we're gonna get that answer simply 1/2, 0 to pi. I'm gonna expand it at 1 minus 2 sine theta plus sine second theta d theta. And then 1/2, 0 to pi. I'm gonna separate it 1 d theta minus 2 sine theta d theta plus 0 to pi sine second theta d theta. Whew. And then you're gonna calculate the rest of work. 1/2. This is a theta, 0 to pi. 2 sine theta, if you take the integral, that is gonna be cosine. Am I correct? So it's going to be cosine. Is it minus or positive cosine? Somebody can double check with me. Yeah, just it's gonna be negative. So negative cosine theta, 0 to 2 pi plus, and then sine second theta, you need to convert it to, okay, this is going to be, I'm gonna write there, 0 to pi, 1 minus cosine second theta. They're same thing. Okay, so 1/2, we have a theta, this is gonna be 2 pi, minus the 0 is a 2 pi, and double negative change it to 2 cosine theta and 0 to 2 pi. And then now we need to take the integral. So it's going to be integral 0 to pi 1. I'm gonna separate it minus cosine second theta d theta. So now 1/2 2 pi, and then 2 times cosine 2 pi minus cosine 0. And this is theta 0 to pi minus. And then again, we have to reconvert it. 1 minus cosine 2 theta over 2. And you still have integral 0 to pi d theta. I'm sorry, a little bit of work, but we can finish up. 2 pi, and this is going to be the cycle of the cosine. So 1 minus 1, it's going to be whole 0. They're going to be whole 0. Check it out. Cosine 2 pi is a 0. Cosine 2 pi is 1. Cosine 0 is 1. So they're 1 minus 1 is a 0. They're all 0. And then if you take the integral with subtract, it's a 2 pi minus 0 is a 2 pi. The next one, yeah, there we go. So here, 0 to pi, I'm going to separate it. And then negative.
Excuse me?
Yes.
Maybe it's not 1 minus, maybe it's 1 plus cosine 2 theta.
Where? This one?
The red one.
The red one? Oh, yeah.
1 plus.
Yeah, 1 plus, my bad. So let me, okay, I haven't done yet, so that's good. So I'm gonna separate it, 1/2 d theta, and then negative 0 to pi cosine 2 theta over 2 d theta. Okay, good. Better? So anyway, we have a 1/2. I'm gonna just adding 4 pi And this one, negative 1 over 2 theta from 0 to 2 pi, right? And then I have a subtract. I'm going to bring 1 over 2 in front, and then you have cosine 2 theta d theta. Almost done. 1 over 2, 4 pi, and then this is 1 over 2, 2 pi minus 0. Okay. And then we have a 1 over 2. This one, we have a 1 over 2 cosine. When you take the integral, it's a sine. And you're going to keep the 2 theta from 0 to pi. So 1 over 2, hang in there. So this is going to be pi. And then 1 over 4, we have a sine 2 theta, 0 to pi. So we have to calculate this last part. So it is going to be 3 pi. Here we go. 1 over 4 sine 2 times 2 pi, 4 pi, minus sine 2 times 0 is a 0. Okay. So 1 over 2, 3 pi. This is going to be 1. This is going to be 0. This is going to be 0, all 0. So the answer, 3 pi over 2 is the area we are looking for. Whew, we got it. Okay, so this is the last version of the formula to find out the area. So you should be okay. So I'm gonna keep going because this is just a long calculation, but I'm pretty sure if you sit down and take a look at it, all the steps, that's definitely you will get the answer. Okay, because I'm gonna do a last question for today. I'm not gonna do everything because the last question is the same thing, just a little bit of variation. So if you guys okay, I'm gonna go down slowly, or you can pause the video, you can come back, but I'm gonna go to one last question today, this one, which is important. Okay, so read that question. Find the area of the region inside of the circle, r equal to 4 times the sine theta inside of this circle, and outside of this circle when radius is 2. So when you draw that, radius is 2. This is the radius is 2 outside, and then when radius is 4 sine theta, it's going to be larger. So if you go to decimal, actually, you can check r equal to, or you can say y equal to 4 sine x. You have a circle above here. So inside of the red, outside of the green. So where is that area we are looking for? This is the area we're looking for. So this is r or sine theta. So anyway, we got it. So now both of them are, I can find out the intersection. So 4 sine theta equal to 2. Sine theta is 2 over 4, which is 1 over 2. Sine theta is 1 over 2. So in the circle, this is going to be from, like, this is the area from 0 to 180 degree. So which theta gonna give you half? You actually gonna find out pi over 6 and 5 pi over 6. So what I'm saying is, many people forgot from the trigonometric functions. So I'm gonna just go to quickly type the unit circle. Actually, I already have it, unit circle. So this is a unit circle, if you remember, long time ago. I'm looking for where the sine theta is 1 over 2. So 1 over 2 is here. 1 is here, 30 degree. So you see that 30 degree sine theta is 1 over 2. And then if you look at 150 degree, 5 pi over 6, oopsie. Sorry, I'm going back. So here, so 30 degree, 150 degree, that's exactly where sine theta is 1 over 2. So you can use a unit circle to find out the theta. So if those who forgot how to find out the theta, so this is the theta. Sine 30 degree is 1 over 2. Sine 150 degree is 1 over 2. As a radian, we have a 5 pi over 6 and 5 pi over 6. So that's your intersected area angle. Here, one angle, second angle. So this is intersected angle between those two circles. So that's going to be your interval. Sorry. So here, from pi over 6, 5 pi over 6. And then everything is a given function. This is f theta or sine theta. And then you can say this is a g theta equal to 2. So we are looking for the between area. So what are you guys going to do? This is the circle. F theta second minus g theta second. Okay, so be careful. This is not going to be 0 to 2 pi because they're intersected angle. So therefore, all you need to do, we have f theta for sine theta second minus 2 to the second theta. So this is, you need to calculate it. So I'm not gonna do whole question. You can finish up, but basically you're gonna find out 16 sine second theta minus 4 and d theta. And then you can separate them. Pi over 6, 5 pi over 6, 16 sine second theta, d theta. Same thing, pi over 6, 5 pi over 6, 4 d theta. So now you can bring 16 here, sine second theta, you can convert it to, 1 minus something, then you can find out the simple answer later. But if I do for you a little bit, 16, and then we have a sine second theta, d theta, and this is a 4 theta, pi over 6, 5 pi over 6. And then sine second theta, as I told you, it's a 1 minus cosine second theta. So again, you're going to convert it this one, 1 plus cosine theta 2, and do all the integral, continue. So I'm not going to finish up because we did the similar work over and over and over and again. So you can finish the rest of work. Try. But the thing is, if you are understanding how to set up this part, right, the calculation is not going to be a big deal. So try this one. And then the same thing, you can try same thing. So it's going to be same thing, subtraction from something to minus. And then the last example 8, we can skip this one because this is a little bit of 3 variables. So I'm not going to do that one. So don't worry. So anyway, that's all about 5.3. I show you 3 different equations in terms of converting from rectangular to polar coordinate equation. Everything is going to give you the same answer. No, whatever you are using, you're going to get the same answer. But depending on the function, the given function, sometimes the first one might be better. Sometimes the second or third equation will be better, but they're all give you the same answer. Okay, so it's a little bit of like a long, work, but definitely you got the concept is a simple. Just calculation is a little like a double work, but I think it should be fine. Okay, so you can finish up 5.3. Okay. And then there are embedded video if you want to watch more, and you can also take a look at the textbook. There's a more practice, but I think I show you all the main idea in 5.3, so you can finish up all the quizzes. Okay, so next session, next video, we're going to continue to talk about 5.4. That one we're going to take a 3 triple integral. So hang in there. So we're going to conquer all the integral techniques in here. Okay, so I will stop recording at this moment. I will hope you guys have a good rest of day, and hang in there and don't be frustrated. It's a little bit of work, but you guys already got this. You already learned each step in calculus 1, calculus 2. I don't want to make you like too pressure, but honestly, this is accumulated idea, right? So check it out. Now you guys have a great mindset. Oh, you got calculus 1, calculus 2. You see the same concept in calculus 3 again. So take a look at that example, and the quiz question should be okay. All right. If you have any question, let me know. Otherwise, I will see you guys in the next video. Bye-bye. Thank you, everyone.